Let me start with a sentence that sounds completely impossible. If you move fast enough, you become shorter. Not in a cartoon way. Not like your bones get crushed. Not like you turn into a small version of yourself. But in real physics. And this is not some random theory. This is a direct prediction from Einstein's Special Relativity, one of the most tested theories in human history. The effect has a scientific name: length contraction. And the scary part is, it's not optional. It doesn't happen because someone is watching you. It doesn't happen because your camera is distorted. It happens because the universe has rules, and those rules force space itself to behave differently when you move close to the speed of light. So today we are answering one big question. Moving makes objects shrink, but why? Imagine you are holding a long metal stick. Let's say it is exactly 10 meters long. You place it on the ground, you measure it with a measuring tape, and you confirm. Yes, 10 meters. Now imagine you take that same stick into a spaceship. This is not a normal spaceship. This is a future spaceship that can go unbelievably fast. The ship starts accelerating. Faster than a jet. Faster than a rocket. Faster than anything humans have built. And then it reaches something insane. 90% of the speed of light. Now picture this. Someone on Earth is watching your ship fly past. They have perfect measuring instruments. They measure your stick while it's moving. And they discover something shocking. The stick is no longer 10 meters long. To them, it has become shorter. Maybe 9 meters. Maybe 7 meters. Maybe even 5 meters. And the faster you go, the shorter it becomes. This is where most people stop and say, okay, that can't be real. But it gets even stranger. Here's the most mind-blowing part. Inside the spaceship, you are holding the stick in your hands. You look at it. It looks normal. You measure it with your own measuring tape. And for you, it is still exactly 10 meters. So now we have a serious problem. Earth says, your stick shrank. You say, no, it didn't. So who is right? In normal life, only one person can be right. But relativity does not work like normal life. In Einstein's universe, right arrow, both of you are correct. And this is the moment where you realize relativity is not just advanced physics. It is a different way reality works. Now let's understand what's really happening. Our brains are trained to think like this. Space is fixed. Time is fixed. A meter is always a meter. A second is always a second. But Einstein proved that this is not true. In reality, space and time are connected. If one changes, the other must change too. And the reason they change is because the universe has one rule that it refuses to break. The speed of light must stay the same for everyone. No matter who is moving. No matter who is standing still. This rule is so powerful that it forces reality to adjust. So when something moves extremely fast, time slows down for it, time dilation. And its length contracts, length contraction. These are not two separate miracles. They are one combined effect. And now we are ready for the real question. What is so special about light that it forces space to shrink? That's what we'll explain in part 2. To understand length contraction, you must accept one strange fact. Light does not follow normal speed rules. In everyday life, speeds add up. If a train moves at 80 kilometers per hour and you throw a ball forward at 20 kilometers per hour inside it, a person standing outside will see the ball moving at 100 kilometers per hour. That feels obvious. But light does not behave like that. If you shine a flashlight inside a moving spaceship, you might expect, okay, the spaceship is moving, so the light should move faster for someone outside. But the universe says, no. Whether the spaceship is moving or not, everyone measures light traveling at the same speed. Right arrow, 300,000 kilometers per second. This is the speed of light in vacuum, often written as c. And it doesn't matter if you are standing still, moving slowly, moving extremely fast. Light speed stays constant. This is not a human rule. It's a rule built into the fabric of reality. And once Einstein accepted this, he realized something huge. If light speed is fixed, then space and time cannot both be fixed. Something must bend. Physicists explain relativity using a simple idea called a light clock. Imagine a small box with a mirror at the top. a mirror at the bottom. A beam of light bounces between the mirrors. Each bounce is 1 tick. Now imagine this clock is sitting still. To a person watching, the light goes straight up and down. Tick, tick, tick. Now imagine the clock is inside a spaceship moving sideways very fast. To an outside observer, the light does not go straight up and down. Because while the light travels upward, the whole clock moves sideways. So the light travels in a diagonal path, like a triangle. That diagonal path is longer than the straight path. So the light must travel more distance for each tick. But here comes the unbreakable rule again. Light speed cannot change. So if the distance becomes longer, the only way for the light to keep the same speed is right arrow each tick must take more time. Meaning, moving clocks run slower. This is called time dilation. And it has been proven by experiments again and again. Now, here's the key point most people miss. If time slows down for moving objects, then the universe has a new problem. Because speed depends on time. Remember, speed equals distance divided by time. If time changes, then distance measurements must also adjust. Otherwise the laws of physics would not match for different observers. Einstein wanted one thing. No matter how fast you move, the laws of physics should look the same. So the universe does something incredible to stay consistent. It changes the geometry of space itself. That's where length contraction comes in. If you move close to the speed of light, then to an outside observer, right arrow your length in the direction you're moving becomes shorter. This is not a trick. It is not because your eyes are wrong. It is because space and time are linked like gears. Turn one gear, the other must turn too. So if time dilates, space contracts. Now let's make this crystal clear. Length contraction does not shrink everything equally. If a spaceship is moving forward, then only the length from nose to tail shrinks. The width does not shrink. The height does not shrink. Only the direction of motion contracts. So if you are traveling to the right, left to right length becomes shorter. Up to down stays the same. Front to back stays the same, depending on direction. This is why it is called length contraction along the direction of motion. And the reason is logical. Because the speed of light rule affects how motion works along the direction you're moving. Ending line for part 2. So now you know the real reason. Length contraction happens because the universe protects the speed of light. But now comes the next question. If this is real, where is the proof? And why don't we see it in daily life? That's what we'll explore in part 3. At this point you might be thinking, okay, this is interesting, but I've never seen a moving car become shorter. And that's a fair question. The reason is simple. At normal speeds, length contraction is incredibly tiny. Even if you drive a car at 120 kilometers per hour, or fly in a jet at 900 km/h, you are still moving unbelievably slow compared to light. Let's put it into perspective. Light travels about 300,000 kilometers per second. That means in 1 second, light could go around the Earth almost 7 times. So even a rocket is basically standing still compared to light. And because of that, the contraction effect at everyday speeds is so small that it becomes invisible. But when speeds get extremely high, nature shows us that this effect is real. Now we come to one of the most famous proofs of relativity. Every day, Earth is hit by cosmic rays from space. These cosmic rays smash into molecules high in the atmosphere. And they create particles called muons. Muons are like heavier cousins of electrons. But here's the problem. Muons are unstable. They decay quickly. Normally, a muon lives only about 2.2 microseconds. That is such a short time that, even at high speed, a muon should not be able to travel very far. Yet scientists detect muons at Earth's surface all the time. But muons are created many kilometers above us. So how do they reach the ground? This is where relativity proves itself. From Earth's point of view, the muon is moving extremely fast. Its internal clock slows down. So it survives longer. That's time dilation. But here's the most beautiful part. From the muon's point of view, its clock is normal. It is not living longer. So how does it reach the ground? Because from the muon's perspective, right arrow the atmosphere becomes shorter. The distance from the upper atmosphere to the ground is length contracted. So the muon reaches Earth before it decays. This is not a story. This is experimental physics. Muons are direct proof that time dilation and length contraction are real. Now let's use a bigger example that feels like science fiction. Imagine a star that is 10 light years away. From Earth's perspective, the distance is 10 light years. Even at near light speed, it takes many years to reach. But now imagine you are inside a spaceship traveling at 99.9% the speed of light. From Earth, your ship looks shorter. But from your perspective, something else happens. The distance to the star becomes shorter. Not a little. A lot. Those 10 light years might shrink down to 3 light years, 1 light year, or even less, depending on your speed. So from your perspective, the star is not as far as it was for Earth. And this is a deep truth. Right arrow length contraction affects the distance between you and your destination. This is why some scientists say relativity provides a shortcut through space. Not by breaking physics, but by using physics exactly as it is. Now, this is where your audience will get excited. People often think interstellar travel is impossible because the distances are too huge. But relativity says distances are not fixed. The faster you go, the more space contracts in front of you. So if humans ever build a near-light speed ship, the crew could travel to distant stars in a reasonable time, according to their own clocks. Even though, from Earth's perspective, decades or centuries might pass. This is not magic. This is the universe's built-in design. And it shows something important. Length contraction is not just a strange idea for textbooks. It is a real effect that happens in nature every day. And it could shape the future of space travel. So we now know length contraction is real. But there's one final mystery. How can two people disagree about length and both be correct? That's the deepest part of relativity. And that's what we'll uncover in part 4. Now we reach the biggest question. If someone on Earth sees the spaceship shrink, but the astronaut inside sees the spaceship normal, then what is the truth? Is length contraction a real physical change? Or is it just an illusion caused by perspective? The honest answer is, it is real, but not in the way we normally imagine real. Because when people hear shrink, they imagine crushing, squeezing, pressure, atoms being forced together. But length contraction is not like that. The object is not being damaged. The astronaut is not feeling pain. The spaceship is not collapsing. Instead, what changes is something deeper. Right arrow the way space and time are connected. Length contraction is not about breaking matter. It is about the geometry of the universe itself. Here is the secret that makes everything click. To measure the length of a moving object, you must measure the position of the front end and the position of the back end at the same time. This is how length is defined. Now here's the shocking part. Einstein discovered that different observers do not agree on what same time means. This is called relativity of simultaneity. Two events that happen at the same time for you may not happen at the same time for someone moving relative to you. This is not a philosophical idea. It's a measurable consequence of the speed of light being constant. So when Earth measures the spaceship's front and back at the same time, that same time is not the same as the astronaut's same time. And because length depends on measuring two ends at one moment, the length changes depending on your motion. This is why right arrow both observers can be correct. Let's say it clearly. Earth observers say the ship is shorter. The stick is shorter. The astronaut is shorter in the direction of travel. Astronauts say the ship is normal. The stick is normal. Earth's distances are shorter. Both are correct because there is no single universal frame of reference. There is no God's camera that shows the true size of everything. Instead, the universe is built so that the laws of physics work the same for all observers. The speed of light stays constant. To make that possible, the universe allows space and time to change. This is not a bug. This is the design. And that is the real meaning of Einstein's discovery. So now we can answer the original question. Moving makes objects shrink, but why? Because the universe has one rule it refuses to break. Right arrow light speed must stay constant. And to protect that rule, time stretches. And when time stretches, space must compress. That compression is length contraction. So the next time someone tells you, objects shrink when they move fast, you'll know what's really happening. It's not a trick. It's not a fantasy. It's the universe showing you that space is not fixed. Time is not fixed. Reality is not what your brain evolved to understand. And the faster you move, the more the universe reveals its true nature. At high speed, even space itself becomes flexible. And that is why length contraction happens.
Subscribe Info Beyond Borders now for more mind-blowing knowledge.